Hello guys, Josh again. So today I'm going to talk about isomers and how to actually draw certain structures based on what type of isomer you're dealing with. And then you can also do the reverse process. If you have an isomer or you have a certain form of a molecule drawn, then you can actually go back and name that compound just using reverse logic. So first I'll start off by explaining what isomers are and the different types of isomers you can get. And for the most part, you'll mainly be working with cis and trans isomers and also FACMer isomers in terms of when you're dealing with even organic molecules, or with FACMer, typically you're gonna be dealing with complex ligand molecules. So first, I'll show you the slide explaining what isomers actually are. So here are the different types of isomers and the different categories for isomers that you can have. Starting from the top, isomers are essentially just compounds that have the same formula but different structures. And you can have this in terms of different orientation, or you can have that in terms of different connectivity and how the molecules actually join together. Examples are structural isomers that basically have the same molecular formula, but there are different ways you can connect those molecules together, and those are one form of isomers. There are also stereoisomers, which are connected the exact same way, but have different orientation or spatial arrangements, which you have to determine by optical activity, such as enantiomers, diastereomers, and all sorts of other types of isomers dealing with that. So when you go down to geometric isomers, that's just different spatial arrangement in which you're dealing with cis and trans and also FACMer. So this next slide I'm going to pull up is going to explain the difference between cis and trans. So as you can see here, these are two molecules that are essentially the same. It's just the way the highest priority group is orientated. So when you're dealing with cis molecules, the highest priority groups have to be on the same side, and trans, they're on the opposite side. So how do you determine the highest priority group? You basically look at the atom that's directly connected to the carbon of the double bond, or the carbon of, or not just carbon, or the metal that you're using. For instance, in the next slide that I'll show, you look at the highest priority group, and if both of the highest priority groups are on the same side, then they're cis. If they're on opposite sides, then they're trans. So in this case, chlorine is a higher atomic weight than hydrogen. Therefore, chlorine is going to be your highest priority group. And since you have two chlorines, if you orient them facing the same side, then you're going to have cis. And if you orientate them on the opposite side, you're going to get trans. So here's the next slide showing you how you can have cis and trans with different compounds that aren't carbon. So here you can see the different combination of cis and trans in terms of when you have a metal instead of a carbon double bond. So again, we see that chlorine is higher priority than nitrogen because it weighs more, it has a higher atomic weight than nitrogen. Therefore, your chlorine is going to be your highest priority group. And in the top left hand, you see that both of the chlorine molecules are facing the same side. Therefore, that's going to give you a cis molecule. And then on the one right next to it, both of the chlorines are opposite of each other. Therefore, that's going to be trans. You can also have cis and trans if you have more than 4 different substituents. For instance, if you have 6 different substituents, if you have 2 and 4, in this case you have 2 chlorines and 4 other ammonias, then if we orientate the chlorines together, then we get a cis molecule, versus if we orientate the chlorines opposite, we get a trans molecule. So make sure you can understand that visualization, because sometimes they're not going to give you just 4 substituents, they're going to give you 6 substituents. So moving on, here's a slide explaining FAC and MER and the different ways you can determine whether or not a property is, or a molecule is going to be FAC or MER or orientated. So here, as you can see, FAC essentially means that you have those 3 substituent groups facing each other. So essentially what you're going to have is all 3 substituent groups all lined up on one side, and then if you orientate that molecule, you see the other substituents line up on the other side. It's kind of similar to cis, except in this case, you're dealing with 3 instead of 2. different substituents. So here, when you identify FAC, it's very easy to identify MER, because MER essentially is just an arc starting from the top to bottom. So if you follow how the molecule is orientated for MER, you can see that there's a slight arc or half circle as you go from each of the green molecules down the line. So you could either visualize it that way, or you can simply just memorize how they're orientated, and then once you're given a question, since you have that memorized, you can then just input the molecules or the substituents correctly on the molecule. So going back to the whiteboard, I'm going to explain some of these questions and explain how you would orientate each substituents based on the structure or based on the stereoisomer that you're dealing with. So guys, here you can see some of the sample questions that they might give you on how to properly orientate different molecules based on the structure that they're giving you. So in this case, we know we're dealing with cis. Therefore, cis means that however we orientate the highest priority groups, they have to be on the same side. And because we know they have to be on the same side, we can simply put our, well, if we're comparing this, we know our substituents are going to be our ammonia and our bromine. Since we know bromine is a higher priority group than ammonia, we know that bromines have to be facing together if this molecule is going to be cis. So if we put a bromine here and another bromine here, they're both on the same side, leaving room for an NH3 here and an NH3 here. And then we're essentially done. So moving on to trans, we know that trans, they had to be facing opposite sides. Therefore, if we put one bromine here, the other bromine has to be opposite of that. Therefore, we can then add our NH3 here, and then our NH3 here. Moving down to this, we have cis, but instead of just 4 substituents, we now have a total of 6 substituents. So remember that now that we have more substituents, the highest priority group still has to be facing the same side. So what's our highest priority group? It's chlorine, right? Chlorine has a higher atomic weight than ammonia, and than the nitrogen in ammonia. Therefore, we're going to have our Cl here, and we're going to have our Cl here, because they have to be facing the same side, leaving room for us to add all other NH3s. So then this will be cis configuration. Then moving on to trans configuration, we know that the chlorines have to be opposite of each other. So if you put a chlorine here and a chlorine here, then we can fill these two chlorines, our highest priority groups, are now opposite of each other. So then we can fill in the blanks. NH3, 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 and then NH3. So the next slide that I'm going to show is going to have a practice problem, or 2 practice problems with FAC and MER. So you can go back and remember the principles of FAC and MER, remembering that FAC means that you have all 3 substituents on the same side, and MER means that you have kind of like an arc. So if you have something like this, MER forms that arc around like that, whereas FAC is just going to have all 3 together like this. So just understand that principle. The next slide will show you those 2 practice problems, and I want you guys to take a stab at that and see if you can get the correct configuration.